So in this third video for the chapter, we're going to apply some of our singularity functions to our RC and our RL first order differential circuits. So let's look first at the step response of an RC circuit. So yes, I'm putting funny pictures at the start of each one. So step response of an RC circuit. So first of all, the step response is defined as the behavior of the circuit when the excitation is a step function, which may be a voltage or a current source. So in other words, it's something like you have a voltage here, you have a capacitor in an RC circuit, and you close the switch. So that is a step function, which you can describe by a amplitude and U of t here, U at t equals 0 in this case. And so there I said that there's my step function being applied, and there's the circuit that we're wanting to analyze. So this capacitor, in the most generic case, already has some kind of an initial condition on it before this circuit is closed. So we'll say that that's V0, and we'll officially say that the voltage the instant before and the instant and after the switch is closed is V0, because the voltage cannot change instantaneously in a capacitor. So then your textbook says, oh, the next step, let's apply KCL, and we get this equation. So I did not get that equation. Well, I ultimately did, but I did not readily see where that equation came from, and from application of KCL. So I'm going to go ahead and look at where that equation came from, because it was not, to me, obvious by just looking at the circuit where that equation came from. So I didn't apply KCL, I applied KVL to the circuit. And when you do that, you have the voltage source right there. And we know it's voltage source U of t, but the voltage source equals this resistor, this voltage drop plus this voltage drop here, right? So it equals IR plus the voltage drop of the capacitor. So remember, we're always seeking to know what this voltage of the capacitor is, which, keep in mind, it is a function of time. So now I am going to, this is a loop circuit. There is one and only current in the circuit, which I in the capacitor is going to be same as I in the resistor is going to be same as I everywhere. But we know that I in a capacitor is C dV dt, correct? So I am just going to substitute that into here. Vs U of t equals C dVc dt times R plus Vc of t. Now it's starting to look like I have a differential equation that we've seen before, except before we had it equal to 0 over here, and now we have it equal to something. This is what we call the forcing function in this equation. So now I'm just going to rearrange some terms. Bs over Rc equals dV dt plus Vc 1 over Rc. I think I can write one more little rearranging of terms, and then I'll probably need another slide. So let's rearrange a little bit more. Just doing the algebra here. And I sort of run out of room on this slide, so I'm going to go ahead to the next slide right here. And that line that I just wrote a moment ago was dV dt equals 1 over Rc. Try to keep that a script V. So that's what I wrote just a moment ago, and for reasons that I knew in advance, I actually like writing it better this way. So I'm just going to change the signs around a little bit there, and now I get that. So I can rearrange a little bit more. Just doing some algebra, I rearrange a little bit more, divide both sides by this term, so I will now get 1 over Vc minus cap Vs on the left hand side equals 1 over RC on the right side. Multiply both sides by dt, and then I'll have dVc equals minus 1 over RC dt. So that's okay. Now the next thing I want to do is integrate both sides. But when I integrate, I'm not going to do a indefinite integral because I have initial conditions in this circuit. So I'm going to integrate from my initial conditions on the capacitor, which is V0, to some time later, since I'm wanting to know what the behavior of the capacitor is at some time later on. And on this side, I have dt right here. So I'm going to integrate from time equals 0 to time equals t. So dv goes on the outside. We're integrating with respect to this variable vc right here. And so I have 1 over something. So when I integrate that, it'll be a natural log vc minus vs. And my limits of integration are from my initial conditions right there. And on this side is minus t over rc going from 0 to t. So these are definite integrals this time. So let's go ahead and plug it in. So plug this one in first. V of t minus vs minus natural log again v0 minus vs equals, well, you're just going to get minus t over rc on this side, because when you put the lower limit on, that will just be a 0. So we're at that right now. So natural log of a minus natural log of b is equivalent to natural log of a divided by b. So if we continue on here, we now have natural log of v of t minus vs over v initial, oops. So this one minus vs, yes, that's an s, minus vs right there, which equals minus t over rc. And just like before, if we want to get rid of that natural log, we're going to take the exponential of both sides right there. So now we'll have v of t, remember that's that we are the solution right here, minus constant vs, and I didn't keep it there the whole time, but always vs has this u of t here, over vo minus vs equals e to the minus t over rc. And so I do a little rearranging of the algebra terms over here to solve for v of t, which is always the value of interest that we are wanting to know, what is behaving in this capacitor as a function of time. And so after I do a little bit of algebra, I will get this vs plus vo minus vs e to the minus t over rc. So I multiplied both sides times vo minus vs. That did that, and then I added this back to both sides, so it moved over on that side. And of course the unit step is occurring right here also. So in the end, you get, remember there's a step in there. So in the end, rearranging one more time, you'll get v of t equals v0, which was the initial conditions for t less than 0, and you'll get, and you can rearrange these terms a little bit more also, but vs plus v0 minus vs e to the minus, and what, yeah, t over tau, so it's a time constant right there, for t greater than 0. There is a equivalent differential equation approach to doing this. It involves learning about what's called a particular solution and a complementary solution, but I don't think any of you guys are taking differential equations yet. I didn't mind talking about it in the natural response of the circuit because I wanted you to understand that you are trying to find a function that's a solution to that differential equation. But anyway, we'll do it this way. Now if that capacitor initially did not have a charge on it, that V0 charge, it's pretty straightforward to see that if there was no V0 charge here, we would get V of t equals 0 before the switch is closed, and then after the switch is closed, you would have the capacitor charging up, which is written as this kind of a equation, t over tau for t greater than 0. So before the switch is closed, there's no charge on the capacitor, and then after the switch is closed, there is a charge on the capacitor, and I'll show you a plot of what. So here's a summary of those two complete solution, whether or not there was initial conditions or not. So that was a pretty big math derivation. Here's if you had initial charge on the capacitor, and here's if you don't have initial charge in the capacitor. So rather than going through all of that math, there's actually a shortcut way. I sort of alluded to it when I said in a differential equations solution you have a complementary and a particular solution. Those are formal math ways of describing the solution, but I'm going to look at it from kind of the way your textbook looks at it, and that the complete response of this circuit, there it is, our complete response right there, is the natural response to it, which remember is the part without the excitation, plus the forced response, which is the part that occurs in that happens to the circuit as a result of applying some independent source. We also say that the complete response of the circuit is the transient part, or this is the part that's temporary or that goes away, plus the steady state response of the circuit. So a transient part is the fact that we have an exponential function going on, and then the steady state is something that occurs like after a long time has occurred. So after a long time you are at this value or approach this value of Vs, and that would be like the steady state response. So let's look at the way that we can get through our shortcut method of having the transient plus the steady state response equal the complete. This is almost a by observation way of writing what's happening in the circuit. So stating what I just said on the other slide in a different way, that you have this, you can describe what's happening in the capacitor by knowing the voltage at time infinity plus the initial condition voltages, and here's voltage at infinity again, and knowing the time constant of the circuit. So that may involve finding an R equivalent and a C equivalent using the methods that we already discussed earlier. But once you know the voltage at infinity, or it could be the current, the voltage or current at 0 or at infinity or at and the time constant, you can solve almost all the circuit problems in this chapter using this formula. And that's actually going to apply even if you're dealing with an RL circuit, which we'll look at here in a moment. And lastly, maybe the switch doesn't close at t equals 0. Maybe it closes at some time t0, in which case all you have to do, because infinity is still infinity, you have to modify the equation a little bit, and now it looks like that. So now let's do an example. So here's the example, good example, all-encompassing example. So the switch has been in position A for a long time, it says, and then at t equals 0 the switch moves to position B. So determine V of t for t greater than 0, and then calculate the value at 1 second and 4 seconds. So we could write ugly differential equations all over the place, but we really don't need to. So for a time less than 0, it's been an A for a long time, and so since we can assume at that point in time that the capacitor is fully charged up right here, and so, or charged to its maximum value that it can charge to, and therefore it's behaving as an open circuit. So if it's an open circuit right here, the voltage that is between A and here is the voltage that's across this resistor, and so voltage in the capacitor at time 0 just before the switch closes, and also just after the switch closes, can be found by just the voltage divider right here. So it's 5k ohms over 3 plus 5k ohms both times the 24 volts, and so that will equal, when you calculated it, will be equal to 15 volts. Okay, so we know that just before we flip the switch into position B, the capacitor charge will be at 15 volts. So then at t equals 0, we're going to switch the switch, and it's going to be in position B. So once it's in position B, we only have this part of the circuit now to consider. So what do we know about this part of the circuit? We know that V in the capacitor at infinity is going to be this maximum value right there, so it's going to be 30 volts. And then we also know that V in the capacitor at our initial conditions time, which is just after the switch closes, is at 15 volts. And the other part that we need to know about the circuit is the time constant for the circuit. We only have these two components here, so it's going to be R times C, with one being half a millifarad and the other half a millifarad and 4 kilo ohms, which will turn out to be a time constant of 2 seconds. 2 seconds. So now we could actually just write out by inspection, which is a lot shorter than doing a differential equation. We can write out by inspection that the voltage in the capacitor as a function of time, and that is actually for t greater than 0, so it's after we throw the switch into position B, will be V at infinity plus the V at 0 plus, or minus, minus V at infinity e to the minus t over tau. So now I can write the whole equation out, that we have 30 plus 15 minus 30 e to the minus t over 2 volts after the switch closes. So now it's just kind of a trivial problem of solving for when t equals 1 second and t equals 4 seconds. So you just substitute that into the equation and get the answer. Now we'll talk about the step response of an RL circuit. We can write a full differential equation with initial conditions in it, like we did for the RC circuit, but I think we will go ahead and use what we've learned from the RC circuit and just apply it here. So what we know is that the current in the circuit, which is the current in the inductor, as a function of time, all of these are function of time, will be the transient response plus the steady state response. So the transient response is going to be a decaying exponential, and the steady state response is going to be what the current is after infinity time has gone by. So transient response is some kind of an exponential where we still need to determine what this value of a constant A is. We know what the time constant is for an LR circuit, so it's L divided by R. We already know that. So what happens in the steady state? What happens when a long time has elapsed here, and it's an inductive circuit? So what happens is that this becomes a short. A capacitor becomes an open after a long time, but an inductor becomes a short after a long time has elapsed. So in the steady state, then, the current steady state current is going to be the source divided by the resistance, because this has become a short. So now we are actually in a position where we can write the complete solution, which has the transient portion plus the steady state portion. What remains to be done still is apply the initial conditions so that we can know what this value of A is. And to do that, we assume that there was an initial current in this circuit of I0. So the initial assumption is that we have an I0. So I at the instant the switch is closed, so at I minus, which is the same as the instant the switch is opened, is this initial value of I0. So that's essentially at t equals 0. So we go over and we use this equation, I at 0. We know has to equal cap I0, the initial current, and we substituted that in. So A e to the 0 plus V source over R. And so from there we can find out that A equals I0 initial current minus V source over R. So we get our initial conditions there just fine, and we can rewrite that equation. And when we rewrite that equation, substituting it now our known values, we get, whoops, got pasted in. We get this as the final complete solution right there. So, which is actually in the form of a steady state solution. Well, this would be the current at infinity time, current from the initial conditions, minus the current at an infinity time, and then our decaying. So it's in the same general form as the RC circuit, except it's an LR, so the constant terms that are floating around are a little different. Remember, in the RC circuit, this was V at infinity, V at initial conditions minus V of infinity. In this case, it's an I equation. We often care about what the voltage is in the circuit rather than the current, and I just wrote current equations, but you can obtain that from the relationship that the voltage is L di dt, and we have I of t. So here I did it for, actually your textbook did it, for when there were no initial conditions on the inductor, and so you just, where's my, every now and then my pen doesn't show up, there it is. So, so L di dt, and so I just did that derivative, and the tau moves to the denominator there, and since the time constant is L over R, you end up with that. But what's interesting to see here is that the current is going from 0 to something that builds, because current will, once you apply a signal, doesn't change right away, but eventually will become the max current in the circuit, correct? Because the inductor becomes a short, and then there will be the max current in the circuit. So if you have the maximum current and the inductor has become virtually a short, what must the voltage do? The voltage must get less and less and less until the voltage across the inductor is about 0. I don't know why your textbook didn't mention it, but the similar thing occurs for the capacitor circuit. While the voltage charges up across a capacitor, when you close the switch, the voltage will charge up, but at the same time, the current will be dropping less and less and less until after a long time occurs, the capacitor is like an open circuit, which is no current at all. So when you look at the voltages and current relationships for the RC and RL circuit, they are complementary to each other. Let's do an example now. So here is a circuit. It says find I of t in the circuit for time greater than 0, and the switch is going to close at t equals 0. Actually, nope, the switch is going to open at t equals 0. So assume the switch has been closed for a long time. So if we're assuming the switch has been closed for a long time, that means that this resistor right here has been shorted out for a long time, and that changes what's happening in this circuit. So when this is shorted out for a long time, this inductor has had time to change to the current that's in the circuit, and it will become a short circuit at that point. So so we need to find the current at that time after this switch has been closed for a long time, so that we will know what the initial conditions are on this inductor. So if this has been closed for a long time, this guy is not here, this is shorted out, and this is shorted out, and all we have is a circuit right here with 10 volts and 2 ohms, and everything else has been shorted out, and I have a current I, which will relate to what the I at time 0 minus is. So I at time 0 minus, which is right before the switch opens up, is just 10 volts divided by 2 ohms, which is 5 amps. So now we have the initial I, and we can, when that switch opens and the circuit changes, this can supply something to the circuit, and the 2 ohm resistor will be in play, and the 3 ohm resistor will be both in play. So we need to find now what happens at I equals infinity. So at time infinity, once again in our new scenario, at time is infinity, this has become a short, but we have these 2 resistors back in the circuit. So I at infinity is 10 volts divided by 2 plus 3 ohms, which was be 2 amps. So we can also get now the time constant for this part of the circuit. The time constant is time equals L over R, which L is 1/3 Henry, and R is 5 ohms. Keep my units pure like that, and that would become 1/15 second. Oh, by the way, I can show you that L divided by R also comes out to be units of seconds. So now we can write the full equation. So it's I at infinity plus, bracket it, I at time 0 minus I at infinity, e to the minus t over tau. We know all of those things for this circuit, so we get a final solution, which so it equals 2 plus 5 minus 2 e to the minus 15t, because of the fraction there, which equals 2 plus 3 e to the minus 15t amps. So what else do I have to find? I just have to find I of t. I don't have to find anything else. So pretty straightforward application of what we just learned. The examples are straightforward for the LR circuit remaining. This was the last example for this section. I don't think it was particularly tricky at all. It looked like it at first, but it's actually not. It's just recognizing that you have things occurring at t equals 0 and t equals 2, which in your exponent here you would just have to put in the t minus 2 for when things happen there. Other than that, for t before 0, the only thing happening is in this part of the circuit. The rest is open. At t equals 0, this switch closes, but this is still open. So this is the part of the circuit now that you have to look at, and it will be there's no initial conditions also on this inductor, so you will get just a straightforward application there of the formulas. And then finally at t equals 2, this one closes. It changes the circuit because it shorts out this resistor. I think you guys can work through that just fine. Like I said, the rest of these examples for the LR circuit are quite straightforward. So this leaves the last section of this chapter. If I pull it over here in my video, this last section of the chapter right here is about the first order op-amp circuits. So I've covered a lot of material in this chapter. You have a lot of concepts that you have to get a hold of. So this is an optional section. You can see by the mark there that this is an optional section, and it has to do with reanalyzing the integrators and differentiators that we already did. I may look at it, but I'm not going to look at it this week. I only gave you one problem related to it, but I think that you can apply what you know quite well to the one problem. But anyway, I should put that in a different video just for the op-amp section, because it will I will exceed a comfortable length of time for a YouTube. So we'll save this for one more short YouTube lesson, which will apply to one homework problem that you have. Okay, that's all.